couple times on there in bold. Do you
Yeah.
mean like big O analysis, or do you mean?
No, I mean being able to write an algorithm, basically.
Just write something.
Yeah, we haven't really talked about order of complexity. We'll do that next quarter. All right, well, let's start with Linux, I guess. No basic Linux commands. I'm not going to give you a million commands and ask you to describe them, but in order to do a lot of stuff on the exam, you want to be comfortable with, basic things like echo, cat for looking at the contents of a file, or more for looking at a file a page at a time. CP for copying, MV for renaming or moving, RM to remove or delete, LS, the idea of switches. You don't need to know OD, but OD is a useful one for looking at a file in terms of its actual byte by byte contents, if you're looking for weird characters and stuff. WC for counting lines and words and characters in the file, date, and so on and so forth. So all the basic stuff that hopefully you've been using for the past 11 weeks plus, in a Unix environment. So I don't think there's anything you need to study for that as long as you've been using these things. Just be familiar with them. All right, standard in, standard out, standard error. So these are I/O streams. And this comes up in a few different ways in this course, but basically, we normally think of standard in as the keyboard. We think of standard out as the display. We think of standard error as the display. So if you write a C program and it uses printf, whatever it prints shows up on your display. If you use getChar, it reads from your keyboard. But more generally, standard in is where things will ingest from. And we have ways to modify what standard in is. Instead of having it be a keyboard, for example, we can use a less than sign followed by a file name, and if we want to command less than file, then standard in is taken from that file. Instead of reading your keyboard, it pulls in character by character from that file until you hit the end of the file, and then it acts as if you had hit Control D to signal end of file. If you use command greater than file, then instead of things that normally go to standard out appearing on your screen, they quietly go into a file. And the file ends up being a copy of what would have been printed on your screen. And if you use greater greater, then it appends to a file, so it doesn't zero the file out to begin with. And in PA5, right, we also saw things like this. So this is for redirecting standard error into a file. So using pipes, you definitely want to be comfortable with piping commands together. So pipes are another way we can modify the nature of standard in and standard out. If you say command 1 and pipe it into CMD2, right? Standard out of this command gets sent to standard in of that second command. And standard one of that, standard out of command 1, right, is whatever's being printf'd or echoed or so on and so forth. And you can, continue this in a big chain, and standard out of command 2 would go into standard in of that next command, and so on and so forth. And we do this to build up more complex, effectively more complex commands, like list all the files that have a name something.c and tell me how many lines are in that listing. So you could say ls*.c and pipe it into wc word count, and it'll tell you how many lines of output there were. So piping things together. Quotation marks. So quotation marks are a little funky in Linux because sometimes they're necessary, sometimes they're advisable, and sometimes they don't make any difference. And occasionally they actually do harm, but usually not. X equals hello, echo $X, X is hello. X equals double quote hello, echo $X, it's hello. X equals single quote hello, echo $X, it's still hello. Those are all the same thing. Right? If double quote hello equals single quote hello, echo cool, well, it says that's cool. If double quote hello equals hello with no quotes at all, echo cool, well, that's cool too. So a lot of times you can get away without quotes, but it very rarely hurts to put in quotes, especially double quotes. Because right, if I was trying to compare hello to a variable and that variable was not equal to anything, I might end up with this kind of situation where it's trying to compare quote hello to nothing, and that looks like a syntax error. Whereas if I had done this, right, then I don't get a syntax error. So double quotes are usually nice. And double quotes, you can still evaluate variables inside. Single quotes will block that evaluation. So if I echo single quote $X, it says $X. And that's probably the big difference between double and single for bash. So if you just want to sort of ensure that things are treated as a string, right, throw them inside double quotes. If you deliberately want to print out things like $signs, you can use single quotes or echo. Right, so I wanted to print out a quotation mark, I can put that whole thing inside single quotes and that works great. If I tried to do that with double quotes, it's weirdness because it doesn't know that that inner quote is not ending my first quote. So single quotes are an easy way to deal with that. All right, back quotes are totally different. If I try to echo back quote hello, I get all kinds of weird back talk, right? So back quotes are basically saying execute a command and then use whatever standard out was from that command in place of this back quote. So if I echo back quote date, it's as if I had said echo Thursday, December 5th, blah, blah, blah. And we use this often when we want to say something like, D equals back quote date. Now D is a variable that's equal to THU DEC 5, 10 colon, and so on. And you can throw pretty much anything you want inside back quotes. If you have a shell script that is doing something and you want to return information from that, you can simply echo that information from your shell script. And if you run that shell script by saying something like, result equals back quote script name, the output generated by that script will go into your variable. Right, so you can use it kind of like a way to do function returns, which is useful sometimes. And there's a few oddities, like if I try to back quote a VI session, that's just weird. Right, so it'll tell me that something weird is going on. I'm not using standard out as a terminal. And so if I trust my VI skills, I can type blindly. And I made a file. And $D is just whatever. Yeah.
Are the backwards totally equivalent to $parentheses?
Honestly, yes, basically. But for this course, the only time we use $paren is to evaluate an arithmetic expression. Okay? I'm going to say use back quotes if you're trying to do something like, D equals the output of date. And save $paren for when we want to do something like x equals 2 plus 3 times 5. All right, so that's the deal with quotes. So shell. So what's a shell? A shell is a program that waits for you to type in requests and then does something in response to them. The shell we've been using in here is called bash, and mostly what it does is it lets you type in whatever, hit enter, and whatever you typed in up to the first space is taken to be the name of a program that should be executed. It will search for a program with that name, and if it finds it, it will run it, and it will pass to it everything that you typed on the line. So when I say gcc-o main.c, and I hit enter, right, I'm sitting inside, a call to fgets maybe, inside some C program called bash, and I type this in, and I hit enter, and that program will take this line of input that I've read, this program called bash, right, and it will look for the first space in here, and it'll say, oh, okay, you type GCC. And it will look for a file called GCC. And if it finds it, it will run that program with this as the list of command line arguments. So it will run that program -o main.c, and then the code for GCC will look at, argv bracket 1 and see that it's a -o, so it'll say, oh, my output file is whatever's in argv bracket 2, that's main, so it's going to open a file called main to write into, and it'll look at this element and it'll say, oh, that's where the source code is, so it'll open it up and start reading in the lines of text and doing whatever it does to compile it. Okay, all of that's being set up by the shell, bash in this case. And I don't think it's in here, but how does it know where to find GCC? Because there's this variable called path, and path has a list of directories separated by colons, and it's going to search in each of those directories for a file named GCC. And while there's nothing in my current directory, and there's nothing in user local sbin, and there's no GCC in user local bin, but there is a GCC in user bin GCC, and so that's the program that the shell is going to run. So it'll do the fork and the execl and so on and so forth to start executing that. Alright, .bashrc is a file which is read whenever bash runs that lets you do some initialization. So anytime that you run the program bash, it's just written to look in your home directory for a file called .bashrc. If it doesn't find it, no problem. But if it finds such a file, it reads each line of this and it pretends that you type that line in. Okay, so it's doing things before you actually get to your bash prompt. It's doing initialization for you. So the comments have no effect. But for example, I set up my path explicitly in here to have, you know, those things in it. I set up aliases so that if I say Eclipse, it does all of that, does the same thing as if I typed in all of that. I set up symbols like Linux, which is a symbol for Nick at linuxengrcs.com, so I can SSH to $Linux. I set up uppercase Linux as the same thing because I seem to make that typo a lot. And I can get to my test account with test and so on. And so whatever you want, right, inside your bash RC, all of that stuff gets executed every time that you run. So I just added some volume commands this morning because my volume buttons don't work well. So I can say V plus and that will turn up my volume 5%. Right? Why? Because it's an alias. And these are all the aliases that have been set up. Now if I just say bash normally, I don't get most of those. But my bash RC sets them up for me. Same thing with my prompt, right? So I set my prompt to be a bracket with this backslash exclamation, which is the line number. Yeah?
Are there any limitations on what you can and can't alias?
No, not really. In fact, you can do things like that. Well, I already broke my alias command, so I can't change that. But yeah, so I just killed my alias command by aliasing alias to something else. But I can unalias it. But I can alias unalias. Right, and now I'm kind of out of luck. So I try to set up an echo and, you know, and I can't unalias that and so on. Now I can log out and log back in, everything's back to normal. If I put that in my bash RC, this would happen every time, then I have to go and edit my bash RC. So in your bash RC you could also alias VI to something else. Well, you can get around that because you can just put in the full path to VI. But yeah, you can get into some mean tricks on your friends with aliases. Right, so oh, that didn't happen. Oh, I think I have GCC alias or something different. Oh, no. My alias command doesn't actually alias. So yeah, you can drive yourself crazy for fun and recreation. So yeah, so bash RC is a way to set up initialization, and in general, there's initialization files for lots of things. Like for example, .git, right, which has git information. That's hidden information. exrc, right? That's a file that gets executed, that gets read every time that you run VI. It will look in there and pretend that you basically typed everything that you find in there. So I turn off my syntax highlighting by saying syntax off in my .exrc. And so these RC files are sort of general startups. All right, so that's bash RC. Shebang's right, number sign exclamation mark, first line of a script. Tells the script how it should be run, tells bash how to run a script, right, what commands you use for it. So normally we do number sign exclamation mark bash. But you know, if I tell it to use bashy to run this script, and then I say go, it'll say, well, I don't know about bin bashy, so it gives me an error. All right, and aliases we just talked about. Alias is a way to set up a name for something else. Typically a command that you don't want to keep typing. All right, processes. I'm not going to ask you to know a whole lot about processes. You should know how to use an ampersand to run something in the background. Control Z stops a process, and then you can run it in the background by saying BG for background, or you can bring it to the foreground by saying FG. And you can kill a job by saying kill the job ID. So if you say jobs, it'll show you jobs in the background. There's a sleep command running in the background. Here's a sleep command that's sitting at my, my foreground. If I hit Control Z, it stops it. And if I look at jobs, I've got my sleep 100 running in the background. I've got sleep 200 stopped. If I say background %2, now sleep 200 is running in the background. Sleep 100 is running in the background. If I say foreground %1, now sleep 100 is sitting in the foreground. I can Control Z it to stop it. I can bring it to the foreground. If I hit Control C, that kills it. Right, it's no longer there. But right now, sleep 200 is running in the background. I can hit Control C. It doesn't affect that sleep 200 command because it's not in the foreground. It's running in the background. And if I just want to kill it, I can just say kill %2, and that kills it. And these are really useful at the command prompt when you're doing things, right? Pull things into the background or run something that's going to take a while. Test PA4 on War and Peace, put an ampersand at the end. It'll go in the background. You can go back to adding comments to your code or whatever. And when it's done, it will tell you it's terminated. And then fork, I don't ask you any questions about fork because I said I wouldn't do that to you. But fork basically lets you clone a process. In a C program, if it executes a call to fork, when it returns, you now have two processes. And they're identical. All their variables have the same values. They're at the same location in the program. The only difference is the return value from fork. So it returns 0 for the child, and it returns the process ID of the child for the parent. And I won't ask you more general concepts about processes. We'll ask you about file systems. So file system, right, it's just, there's a hierarchy of files starting with slash. Slash is the top level directory, and it mostly contains subdirectories. A few files. Right, and a few links. So like backup is a link to my backup flash drive, or my backup hard drive. Flash backup's a backup to my flash drive, and so on. But mostly directories, right, including this directory called home. And if I look in there, then there's some directories underneath that, including my home directory. And if I look in there, there's files, there's directories, and so on. So it's this, standard hierarchy of files that we're used to. And a period always means your current directory. So right now I'm under home Nick. If I say cd dot, that's like saying cd/home/Nick. If you say ./go, that's like saying /home/Nick/go. Right? You're specifying exactly where this file named go is that you want to execute. And when you look at the path, since it has a dot in the beginning, it means if I just say go, the first thing it's going to look for is a file named go in dot. Well, dot is my current directory. So right now I'm sitting in home Nick. If I say go, it runs home Nick go. If I'm sitting in a different directory and I say go, it'll say there's no such file, because it's not in dot anymore, because dot is now /home. So dot's kind of a relative directory. And then dot dot means your directory above you. So if I cd dot dot and I print directory, I'm under /home. If I cd dot dot and print working directory, I'm under /. So that moves you up. And you can't move above the top, it just leaves you at /. And so I'm using cd and pwd already to like look at my directory, look at what directory I'm in, or to change my directory. So I can ls dot dot, so I can current directory dot dot /guest, and it's like moving up one level and going down into guest. So now I'm in home guest. Right, so probably nothing too startling there. All right, so hidden files. Hidden files are no different from any other file. If I do an ls, I have an examples.desktop in here. But if I do an ls-a, I see more files. I see a .bash rc and a .config and a .bash logout and so on. They're perfectly legitimate files just like any other file. The fact that they begin with a period means that ls will not show them to you by default. Okay, so these are called hidden files. And there's nothing different about a hidden file to a non-hidden file other than the fact that ls treats it differently. But it's convenient because chances are every home directory is going to have a .bash rc and a .bash logout. And every directory that you use git in is going to have a .git directory. And we don't want to deal with these files. We don't want them visually cluttering up our directories when you know, we're working on a project or something. We say ls, we want to see our source code. We don't want to see all these other files. So it's just a convention to keep them hidden unless you say ls-a, which says show me the hidden files. All right, permissions. So let me fix my Go script. So remember, when you do an ls-l, you get this sequence of things in the beginning: rwx, r-x, r-x. Right? These are our permissions on files. So the world's broken into 3 camps. There's the owner, that's you. There's the group, which for you is anybody whose group is students, which is mostly other students. And then there's the world, which is anybody not yourself and not in your group. And for each of these you can say, are people in this category allowed to read this file? Are they allowed to modify or write the file? And are they allowed to execute the file? And the permission bits are just 1s or 0s. Right, so if I set my permission bits like this, it means the owner can read and write the file but not execute it. People in the group can read but nothing else, and everybody else has no access to the file at all. If I want to set this permission on a file, you take this and you write it in octal. So it's a 9-bit binary number, but just write the octal code for each of these, and that's a 640. So if I said change mode 640 some file, it should give me those permission bits. So change mode 640 go. Now if I look at it, owner has read write, group has read, world has none. And so if I try to execute it, it says permission denied. If I If I change the permission to 740, right, the 7 means I have read, write, execute permission. The 4 means people in the group can read but not write or execute, and the 0 means nobody else has any access to it. Now if I try to execute it, I can. Alright, so here's a weird permission. I said the owner has no access to this file, but people in the group have read, write, execute, and everybody else has read, write, execute. So if I try to look at the contents of the file, it says permission denied. If I try to edit it, it will open up my VI session, but it doesn't show me any contents because I don't have permission to read the file. And I certainly can't execute it. But because I'm the owner, I can change the permission bits back to something where I do have access. And if I try to write into that file, I don't have permission for that either. And if I try to remove it, it'll tell me, well, you don't have write access to this file. Are you sure you really intend to delete it? And since I'm the owner, I can say yes, and it'll go ahead and do that. So that's a basic permission scheme. And that's really, underpins the heart of security in Linux systems. You use file permissions to protect files, and files basically are used to access hardware resources, network connections, things like that. So that's a big part of how things get locked down. All right, so variables, we already talked a little bit about setting variables for values, right? X equals hello. Echo X is just an X. Echo $X is the value of the variable X. X equals 2 plus 3. Echo X is still an X. Echo $X is 2 plus sign 3. Okay, it's a very, very, very literal system. So if you want to do arithmetic, take your expression, put it inside $paren. And now it'll actually set X equal to the result of that expression instead of just the string 2 plus sign 3. So using $sign to evaluate the value of an expression. Yeah, that's weird. So exporting variables. So someone asked me about this morning. We didn't really talk about this a whole lot, but this is something you should know in general. It's not on the test, but you should know this in life. Okay, oh, I got rid of it. Okay, so here's a really simple script. It just says the variable X has the value, and then it prints out the value of X. So I can say X equals hello. And if I say echo variable X has the value X, it'll tell me variable X has the value hello. Well, so I have this script called go that also says echo the value of X has $X. But if I run that, it tells me variable X has the value, blah, nothing in there. So even though I know that X has this value, my Go script doesn't know that. Okay, we can think of these variables effectively as being like local variables. X has a value right here at my command line prompt. But if I run another program or I run another script, X is a new variable X. It doesn't have the same value. It's a completely different variable. Okay, if I want to make sure that when I run a script it sees this variable x, we can make it basically global by saying export x. Okay, now if I run my Go script, it shows me the value of x. And if I give x a different value and I run Go, it shows me that different value. So it basically makes the value persistent as I create new shells.
So will that export X anywhere in the system or just in that directory? How does that work?
It's independent of directories. So x is a shell variable, right? But if I create a new shell by saying bash, right, it still has that value. Whereas, you know, if I make y a variable and I start a new bash shell, y is just, you know, it's an uninitialized variable. So when you say export, it says if you create a new shell, give that new shell the value of this variable too. But it doesn't matter what directory you're in or if you're doing this from a script or anything else. All right, and then built-in variables. So when you run a script, $1, $2, $3, these are the command line arguments. Make sure you know the difference between command line arguments and program inputs. Okay, command line arguments are something like this. That's the name of my program. There's my bash prompt. Type my program name and I put some information on the same command line. Those are command line arguments, and I get to these typically through argv bracket 123 or $123 if this was the name of a script, and so on. Program inputs, you type in the name of your program and you hit enter, and it says, you know, give me a number and waits, and you type in a number. Type in the number 2. Okay, and that's something that you're doing with, you know, fgets and maybe scanf and stuff like that. Okay, command line arguments you just specify in the same line where you typed in the name of the program. Program inputs, you run the program, and while it's running, it's asking you to type in inputs. Two totally different paradigms. So, right, so we can print out the value of $1, 2, and 3. I say go, this is fun, then those are just equal to my arguments. If I just have one argument, then $1 is equal to that argument, and $signs 2 and 3 are just blank. If I happen to use quotation marks, then $1 is that whole quoted string. $2 and 3 are blank. So without quotes, everything gets broken up at the spaces. And it doesn't care if these things are numbers or words or symbols or things like that, for the most part. Although if you use wildcards, things change, right? Because an asterisk gets interpreted by the shell as a list of files, and then it's as if I said go followed by a list of files.
Would $0 be go? Or is there
So yeah, let's play with this. Bless you. So let's look at $0, right? $0 is /go, so it's the program name. And if I echo $0 right now, I get bin bash. Why? Because I'm sitting in a program called bin bash. Right? This is what I'm running. And it was run without arguments. And $number tells you how many arguments you have. So if I say go hello, $number is equal to 1, because I only have one argument. $$ is your process ID. Right, so 11192, that's the process ID on my bash shell. That's what $$ tells me. And $? shows me the return value from the previous command. So if I do something goofy and I look at $? It's non-zero. It means I probably had an error in my previous command. If I do it again, it's showing me the return value from my echo statement, which was a 0. Right, so it's always the value of the previous command. If you've done 270, this is like the skip instructions. When you write assembly language, they're based on or the conditional branches rather, they're based on the condition codes from the last instruction. So whatever the last command was, the return value from that is what gets echoed. Right, and we can exit with a code in a script, and that will be the return value from the script. So if I say exit 42 at the end of a script, and then I look at $? I see a 42. That's another way you can pass a value back from a script as kind of like a function return. But it's just an integer, a small one. All right, Zenity. You're all Zenity experts, right? Because you've been doing this, and so basic dialogues. I'm not going to ask you for nuanced details, but you know, you should know that Zenity is a way to create a GUI type object, and that you basically say Zenity dash dash, and you tell it what kind of thing you want, an entry box, a text box, a calendar, whatever, right? And then there's a billion switches you can put on there to modify the behavior of it. And mostly Zenity produces on standard out something related to, you know, the user interaction. So if you pick a calendar date, it'll print out the date in some format, and you usually grab that by throwing your Zenity command in back quotes. Do you know the GCC command? We talked about GCC. All right, so know how to use GCC. Mainly, make sure you know how to specify an output file. Right? Or I could say GCC inputs -o output. Or I could even say GCC inputs -o output and more inputs. Right, all of these are valid. The important thing is that -o is followed by the name of an output file. If I say GCC-O inputs, then my first input file becomes the output file, and it clobbers my code, and you've lost a C program. So know about the output switch. If you use a -G switch somewhere, that lets you compile with support for using GDB, the debugger, which we'll do a lot more with in winter. And if you say GCC-C file.c, that compiles it into a file.o. It's like halfway compiled in some sense. It doesn't give you an executable program, but it gives you something that you can put together with other .o files to make an executable. And this mainly comes in with make files when we want to do sort of partial compilation. All right, GDB, know the basic commands for GDB. So how to compile with a G switch, GDB executable to start GDB itself, start to begin executing your program. Before you start your program, you can say break and put in a line number. You can say break, put in a function name, and when it gets to that location in your program, it will stop executing and come back to GDB and ask you for more instructions. And you can say step, or you can say next, right? So next is a step over. So function calls get treated as one instruction basically. Step is a step into, so if you step right before a function call, it stops at the beginning of that function. So that's for single stepping your code. You can print the values of variables by saying print. You can say continue to say keep running until you hit another breakpoint. You can say watch variable, and it will stop when that variable changes value. You can say list to look at your source code. And I think that's the summary of all the GDB stuff we've done. And so just kind of be familiar with the basics of that. Make files, let's see. Do I want to rush through this? No, we'll talk about this more leisurely. We'll talk about make files tomorrow. tar is really just creating an archive. It's just 3 commands you need to learn. We'll put those up. Regular expressions, I'm not going to ask you to go crazy with regular expressions. There's time for that in the future. Same with sed and awk. You should know like the basic idea. Sed lets you process things a line at a time. Awk lets you take a line of text and break it up by fields. But I'll show you a couple of sample uses, and that'll be the worst that you'll see on the exam. So we'll finish through those tomorrow, and then bash programming you've been doing all quarter, so we'll just kind of run through that, but there's not a whole lot to say there. And then C programming, you've been doing that all quarter too, so so look at those, come with questions, but it's pretty much just what it says. So we'll finish this up tomorrow.